Welcome to Steam Engine. Today, we stand close to machines that once pulled entire factories, coal mines, and battlefields forward. These are not pretty engines made for display. These are slow-moving mechanical blocks built for maximum torque. Not flashy speed, but pulling force as dense as a sledgehammer. You will hear steam hissing through valves. You will hear pistons pounding in a steady beat. You will hear diesel knocking deep at low RPM. And you'll hear a V12 roaring like thunder inside an enclosed room. We will meet a Swedish crude oil engine running at 400 revolutions per minute with giant flywheels holding the rhythm. We will meet a two-stroke Detroit V16 screaming under heavy load. And we will meet a museum steam engine awakened step by step. Oil goes in, pressure comes up, valves open, the flywheel starts to roll. In each segment, I will explain the mechanism so you can clearly hear the engineering. Swedish crude oil engine. 35 horsepower that runs steady to live longer. In Malå, Sweden, a 35 horsepower crude oil engine was born to do one thing: turn steadily at around 400 revolutions per minute. In the first half of the 20th century, with many regions still lacking strong and reliable grid power, this kind of machine functioned like a community power station. It drove generators, it ran water pumps, it spun sawmills, it blew air into furnaces, and it carried a full load of agricultural work. It was not polished at all. A thick cast iron body, large bolts, a frame heavy as a stone pedestal. But once it falls into rhythm, its deep, even firing sounds unmistakably real. No rush, no stumble, like an old factory working by discipline. And that is when people always ask one question: how can 35 horsepower drive so many jobs? The key is the flywheel. Two large flywheels turn like two energy storage devices based on rotational inertia. When the piston hits hard, the flywheel takes the udar. When the piston reverses direction, the flywheel releases gradually. It keeps the shaft smooth so belts do not snap and the machines behind it do not hesitate. Because it burns crude oil, it is also designed to burn heavy, low-quality fuel. the kind that is easier to find in remote places when good gasoline is still scarce. In return, starting demands care. Preheat. Open the fuel manually. Control the temperature in the combustion chamber, then let it catch. Once it is running, it reveals the beauty of early industry. Simple, heavy, durable, and working as if it never gets tired. Right after that deep beat, the atmosphere changes completely. There is another kind of engine that is not unhurried like this. Detroit V16, the scream of a heavy load. If the Swedish crude oil engine is like an old craftsman working with steady hands, the Detroit diesel V16 is like a team of 16 miners heaving together at once. This is a two-stroke engine. Instead of intake, compression, power, exhaust, taking 2 crank revolutions like a 4-stroke, it completes a power-producing cycle in every revolution of the crankshaft, 2-stroke. That is why, when the throttle opens, the exhaust note shoots higher, sharp, almost a scream, and the base frame vibrates like someone is pulling steel tight.
Let's get you a better seat.
You only need a few seconds to understand what it was built for, to carry a load, not to sound smooth for show. From that sound, we look into its structure and how it lives on fuel. V16 means 16 cylinders arranged in a V. Many versions were built by pairing 2 proven V8 banks, then sharing a common crankshaft and intake and exhaust systems. Its power range can run from around 450 to more than 2,400 horsepower. That is why it often sits on ships, large generator sets, and heavy mining machines. In those places, the priority is continuous pull, thick torque, enough cooling, stable oil pressure, and fast repair when needed. Mechanics listen to measure health. A missed beat points to fuel suspicion. A change in smoke color points to combustion suspicion. A rising temperature means to stop immediately. After hearing the Detroit V16, People want a different tone, a quieter kind of power, as steam begins to hiss inside a museum room. A museum steam engine, the flywheel wakes up. Inside the exhibition hall, the steam engine has stood still for decades. A flywheel as large as a mill door, a heavy bed plate. Connecting rods are polished with oil. Before they run it, the technicians follow the same lesson. Check the bearings, oil the points, test the valves, recheck the steam lines and every joint. This is an exhibit, so every motion is slow and sure. There is no sudden steam admission. Steam is introduced gradually, so the metal warms evenly. Pressure rises little by little. A thin hiss spreads, then thickens around the room. When the pressure needle reaches the threshold, the operator cracks the main valve. The flywheel trembles lightly, then begins to roll. Steam enters the cylinder. The piston works in a double-acting cycle. Double-acting. The connecting rod pulls the crankshaft, and each push adds a little more to the rotation. The flywheel does the rest. It stores momentum. It pulls the machine through the dead centers, TDC and BDC. It turns jerky thrusts into smooth, circular motion. A deep chuff echoes in a steady rhythm. The floor vibrates for real under the visitor's feet. In that moment, you understand why steam once fed an entire era. Turning factory line shafts, running pumps, pulling hoists, driving ships and locomotives over long distances. The steam sound hangs in the air, then gives way to something completely different. The Meteor V12 from a tank, hotter and more ferocious. Rolls-Royce Meteor, the heart of British tanks. Meteor was not a tank engine from the ground up. It was the Merlin, an aircraft engine adapted for the ground. The supercharger was removed. The compression ratio was tuned down to 6:1 to optimize mechanical durability, make repairs easier, and reduce production cost. Engineers from Rolls-Royce, Rover, and Leyland all took part in this project. It was still a 27-liter V12, but the priority shifted to heat tolerance. dust tolerance, and long running inside a cramped engine bay. They chose the Meteor because a tank that stalls in mud is not just a breakdown, it becomes a target. And in this story of cutting back to survive longer, you can see the truth clearly. On the ground, pulling power matters more than advertising. In military configuration, the Meteor delivered around 600 horsepower at 2,500 revolutions per minute and torque around 1,450 pound-feet. That was enough to pull a heavy steel mass across trenches, climb grades, and change direction on soft ground. At low throttle, the growl is deep and steady. Open it wider, and the heat blows out like a coal furnace. Mechanics watch oil pressure and coolant temperature. The brilliance lies in simplification. Fewer auxiliary systems, fewer small failures, fast maintenance between operations. Meteor turned many British tanks from sluggish into mobile, and more importantly, it made crews believe they would still have an engine to run again tomorrow. That mindset leads straight to a diesel job site legend, the Cummins NTA 855. Cummins NTA 855, the packhorse of generators and job sites. The Cummins NTA 855 is not famous for being loud. It is famous for working relentlessly day and night, where stopping is not allowed. This is a 6-cylinder inline diesel, around 14 liters, 855 cubic inches, 4-stroke. The large displacement helps it make high torque at moderate RPM. That fits generator sets, tugboats, excavators, and mining trucks. The easiest way to understand it is how it breathes. A turbo forces more air into the cylinders. An aftercooler cools the intake charge so it becomes denser, burns cleaner, and runs more efficiently. In industrial trim, the NTA 855 typically sits around 240 to 450 horsepower at 1,800 to 2,100 RPM. But the more important number is torque. When a heavy load hits, it does not sag. It holds its rhythm. A major reason is Cummins' PT fuel system, control through the legendary PT, pressure time fuel system, which self-adjusts fuel delivery according to pressure and speed without complex electronics. In remote areas with little diagnostic equipment, that clear mechanical logic is a lifesaver. Mechanics also like the NTA because it is easy to overhaul. Replaceable cylinder liners, convenient access to major assemblies, short downtime in the yard. On top of that, Cummins' parts and service network is broad, so owners are less afraid of breaking down with no parts. After hearing the NTA 855, many people want to see something older, a hot bulb engine that must be heated directly before it will fire. A 100 horsepower hot bulb engine. Heat it first, then it will agree to fire. Some engines do not begin with a key, they begin with fire. With a 100 horsepower hot bulb engine, the operator must use a blowtorch to heat a metal bulb attached to the combustion chamber. It sounds crude, but it is an entire ignition system. When the bulb is hot enough, fuel is injected and self-ignites from heat and compression, with no spark plug needed. This method was made for places of scarcity. No electronics, no complicated systems, only fuel and the knowledge to wait for the right temperature. Its biggest advantage is stubborn durability. The block is mostly thick cast iron. The crankshaft is large. The pistons are big. It runs lat-hour RPM, so wear stays low. It can burn many heavy fuels like heavy oil or paraffin, which are easy to find and cheap. Once it settles into rhythm, it does not scream. It goes puff, puff, deep and steady, each beat like a solid shove. A heavy flywheel keeps the shaft turning smoothly. That is why it can pull a stable load, pumping water, driving a generator, pulling agricultural equipment or workshop machinery. But hot bulb engines also demand discipline. Heat too little and it misfires. Heat too long and you waste time and risk overheating. Experienced hands read the metal color, listen to compression, and smell the fuel to know whether it is there yet. And once you have seen a machine that must be convinced by heat, you will understand why a revival after an entire century, like the Fiat 1911, can give people goosebumps. Fiat 1911, 12 years to hear one explosion. Among all the machines brought back to life, the Fiat 1911 story may be the one that holds people's breath the longest. This was an early speed record project, carrying a massive 28.4-liter four-cylinder engine. It did not need maximum power at extremely low RPM. It made force through an enormous piston stroke and a large rotating mass. The specifications sound unreal. Around 290 horsepower at 1,100 revolutions per minute. Torque near 384 pound-feet, a 190mm bore, and a 250mm stroke. Even the drivetrain is old to the bone. Twin-chain drive, a body weighing nearly 1,900 kilograms. But what stays with you is not the numbers. It is 12 years of restoration. More than a decade of taking it apart, cleaning, remeasuring, remachining, and finding ways to replace broken parts when replacements barely exist. Because with a century-old machine, what kills it is often not a big failure. It is seized rust, sludge turned to stone, hardened seals, and worn friction surfaces. The people doing the work have to be patient enough to accept progress measured in millimeters. On the day of the start attempt, the atmosphere feels like a ceremony. The starter pulls, a few hesitant beats. Then the engine kicks alive with a thick, rough explosion, like a hammer striking the floor. Smoke bursts out. Then the rhythm slowly stabilizes. And when it finally holds steady, you realize what has come back to life is not only a car. It is an entire era's faith in mechanics. Right after that, the story returns to the sky, where the Bristol Hercules carries wartime power into the air. Bristol Hercules, the enduring strength of the sky. The Bristol Hercules is one of Britain's most formidable aircraft engines of World War II. A 14-cylinder radial in 2 rows, air-cooled, around 38.7 liters of displacement. The difference lies in the sleeve valve mechanism. A sleeve valve replaces the poppet valve that helps intake and exhaust breathe better, and the engine runs smoother once it is warm. Depending on the version, Hercules ranged from over 1,200 to above 1,700 horsepower, enough to lift warplanes into the air, fly far, and carry heavy loads. Mechanics valued it for durability. Run it at the right temperature with the right oil and the right rhythm, and it is as stubborn as stone. And for today's audience, that radial sound is not just noise. It is the memory of an era when power had to be trustworthy, because in the sky there is no room for error.